perturbances, but when we're in the tropics, we need to look at convection to understand precipitation. And rain gauges, they're never going to be sufficient when we have such a complex terrain. So we can't really understand the full complexity of the spatial and temporal features of the precipitation just on rain gauges. On the other hand, we have satellite data, in particular infrared satellite data. There's many other products as well available, but the infrared satellite images are the simplest ones, and they actually provide a very good temporal and spatial resolution to identify the convective events. So if we can do that in terms of convective events, we can probably transfer that into precipitation and estimate the distribution on the one hand. And on the other hand, that is also going to be very useful to understand how convection works. There's still many things about convection that we don't understand. We still need to parameterize it in climate models. And these parameterizations are not perfect, or far from perfect yet. So this region of Northwestern South America is like a very good laboratory for understanding how convection works and different types of drivers for convection, given that we have this complexity in the topography and coastlines. So how do I identify these convective events? So when we have these kind of clouds, this convective cloud, a cumulus cloud, we know that convection implies a relatively large area of what I would call a low cloud top temperature. So these clouds, of course, they deepen in the vertical, they grow, and that means that their tops are going to be cold. So we should be able to see a low cloud top temperature, an area of low cloud top temperature. But not just that, we also we would expect to see at least a fraction of that to be not just low, but very low, which I haven't defined exactly what low and very low means, but just in very qualitative terms, we expect that because we have these strong updrafts that may produce even overshooting at the cloud top. So that must generate some very low cloud top temperature above of this larger area of low cloud top temperature. And there's a third aspect important to identify these events, and this that you always expect a rapid deepening of the cloud. So these convective clouds, they don't develop in long time scales, but it's really in short time scales, about the order of minutes or hours. And that means that there must be a rapid deepening of the cloud, and that implies a steep decrease in the cloud top temperature. So over time, you expect these cloud top temperatures to decrease very fast. So if we translate that to what the satellite sees, geostationary satellite sees. In this case, I've used GOES 13, which is just on top of this part of South America. So it's very convenient to study convection in this region. This satellite was operational between 2011 and 2017. So we have 7 years of brightness temperature that we can estimate from this satellite. And this brightness temperature, of course, it's kind of a proxy for the cloud top temperature. We expect that it's going to represent the actual temperatures of the cloud. It's not going to be perfect, but more or less it's going to be good. This IR band from GOES 13 has about a 4-kilometer resolution, and it's available every 30 minutes for this part of the world. It's not something new. So many previous studies have used infrared images to identify convective systems. It has been used a lot for mesoscale convective systems in the past, and to look at distributions in a larger scale. The advantage now is that, well, we have every time better and better resolution of these products, so we can go into finer details. So this would be an example of one of these images over this part of the world, where I've colored in pink a particular threshold of temperature. So temperatures below that value are in pink, and then that would be what I call these low brightness temperatures or cloud top temperatures, and then the green temperatures would be the even lower brightness temperatures. Now, in order to really make this work, to identify these systems in an automatic way, you actually need to grid this data, so to make averages over a larger grid, not just at 4-kilometer resolution, because that's probably too fine. You need to make it a bit coarser, also because you don't want to have too much noise in there. you don't want to have too many small scale features appearing there when you identify the systems. So what I do is I grid the data to a 16 times 16 kilometer square grid. That means about 4 grid points on each side. And then you get this kind of images. And then you have a rectangular grid, which is easier to work with, to track systems and to identify them. You always look at the same points, whereas with the satellite, it's something that's kind of changing all the time. So you need that initial step. And then, well, you need to define your thresholds. What is a low temperature? What is a very low temperature that you want to identify for these convective events? And well, of course, you have to try different thresholds, and you have to look in the literature what other people have used. So I've based a lot of these thresholds in what Dave Adams has been working on in the Amazon previously. And finally, I came up with these values. So the low temperature is 235 Kelvin. So if you find a region of brightness temperatures below 235 Kelvin, that's a possible convective event. But then you need, within that region of 235 Kelvin, you need also a very low temperature, so below 210 Kelvin. So for example, this system here would not be considered a convective event because it doesn't have these very low temperatures. But this one here would, or this one as well, or these ones here. And then the other important condition is that you need a rapid decrease in brightness temperature, and that I've used 50 Kelvin in 2 hours. So you need, for this particular system to be considered as a convective system, you need to be able to detect a decrease in 50 Kelvin in 2 hours within a 3-hour time window. And then I also use trim precipitation data, which is available in 3-hourly intervals, just to double check. That doesn't really make a difference because it's usually always there, but it if it's the same system that appears every half an hour. And that allowed us to track 77,000, a bit more than 77,000 deep convective events. That's about 30 events per day in this region, which is kind of realistic. It's probably we're not capturing all of the systems, but I think it's kind of close to the actual number of convective systems that occur in this region. Okay, so these are the green region is below 210 Kelvin, the pink region is below 235 Kelvin. So now to the results. The spatial distribution. So once we have identified that many events, we can do a lot of things with that. And the first thing is to look, where do these events occur mostly? So we can look at it in 2 ways. So the left panel here is just looking at the area of cold cloud top temperature, so below 235 Kelvin. That kind of reflects the entire area that the convective system influences, not just the peak of it. And then we can look at the minimum cloud top temperature for each convective system, and that really pinpoints the point where it's most active or most intense. So you see that the distribution of these kind of hotspots, what I would call hotspots of convection, are the same in both. These are just more precise, and it shows that there's, first of all, these hotspots are always over land, except maybe for Lake Maracaibo, which is, well, it's not exactly land, it's not ocean neither, but it's a lake. But otherwise, they are all over land, these hotspots. So that's what you would expect, because over ocean, you expect the convection to be more spread out and not have any preferential locations to occur. But over land, this really means that they are fixed to several topographical features. And the other interesting feature here is that these hotspots are always on the west flanks of the mountains, except for 2 places. So if you notice, this one is on the westward flank, this one as well. These ones here along the Pacific coast as well are on the west flanks of the Western Cordillera here. This one here is also on the westward flank of this small hill. Along the Sierra Nevada as well. This might be more like a sea breeze coming from the Caribbean coast. But then you have these two ones. So this one here along the Catatumbo region, this is somehow connected to the Maracaibo Lake. This is on the eastern flank, so that's an exception. And this is another exception here on the middle Magdalena Valley, which is actually on the eastern flank of the Central Cordillera. Now, what about the size of these systems and how long they survive? So this shows the size of the systems in square kilometers, in thousands of square kilometers, and this shows how long they are on average. So it's a mean duration of these events. And the first thing that's clear here is that those hotspots that occur over land, they have actually small and short events. So you don't see the larger events and the longer lasting events are not located at those hotspots. They are actually in other regions where they are more spread out. But then, and then you see what we expect. There's a lot of large and long-lasting systems here in the Pacific. That's what has brought so much attention to this region. Also in the northern part of Colombia. So this is the lower Magdalena and Cauca valleys. And you also have large systems here along the Orinoco and Amazon basins, but interestingly, they are large, but they don't seem to be as long-lasting as the ones in the Pacific or to the north. So that's an interesting contrast that is worth some further investigation. What about the seasonal cycle? So this would be the distribution of all the events within the entire region, and then you see them here by month. And what you can clearly see here is the ITZZ migration. So it's very clear that you have the southernmost position of the ITZZ here at the beginning of the year, and then it goes north towards the boreal summer, and then again goes back south. So you really see that migration of the ITZZ, which is, it's known that that's what defines the seasonal cycle of precipitation in this area. But something interesting, or it's kind of obvious, but it's worth mentioning, is that those hotspots that we found in the annual mean distribution, they are still there for the different months. They just are on or off depending on where the ITZZ is, but they don't move around. So that just confirms that these hotspots are really related to the topographical features, to the lower boundary conditions that are found here. Now, this seasonal cycle, you can look at it in more detail. I'm going to try to go fast here because otherwise I'm going to spend too much time. But essentially, I define two indices that allows us to look at. There's two main features of the seasonal cycle in this part of the world. Usually, you look at if things are bimodal or unimodal. So if you just have one peak of precipitation or convection during the year, or if you have two peaks of precipitation. And that also compared to the mean value of precipitation. So this in the index here, S0, it actually indicates how large the mean is compared to the seasonal amplitude. So these regions, for example, here with this box number 2 or 3, or here below in the Amazon, where S0 has a large value, that actually indicates that the mean is large. So the annual mean value of convective events is large compared to the seasonal amplitude. So there's essentially convection all year round, despite also being there being a kind of seasonal cycle there. And then to the right here, S1, it actually compares the contribution of the annual, or so the what would be a unimodal regime with just one peak, yeah, that's just the annual periodicity, to the semi-annual periodicity with two peaks during the year. So whatever is blue here means that there is more of a semi-annual or bimodal regime seasonal cycle. And whatever is red is more like a unimodal cycle. So it's clear that you have to the north a more unimodal, which is what you would expect because the ITZZ just reaches there once a year. And then in between you would have a bimodal distribution because you have the ITZZ once going to the north, once going to the south. And to the south, again, it starts becoming red, so just more unimodal. But then you see that there's some exceptions like the Pacific, which is more unimodal. And also there's essentially convection throughout the year. can actually look at that in terms of the specific region. So for the box number 2, you have this distribution. You see that there's convective events throughout the entire year, but there is a seasonal cycle with just one peak here in the months of maybe July or August. And then if you look down here in the Amazon basin, you see that the seasonal cycle is much more important relative to the mean. And you have a bimodal distribution of events. So that's why this region ends up being blue. And this is very interesting because we know that precipitation in this part of the country of southeast and east of Colombia, it has a unimodal distribution. So we know that there's only one peak here in precipitation, which is usually around the middle of the year. But we find here that actually the convective events have 2 peaks. So there's something that doesn't really match there between convection and precipitation. So either we are missing some of the convective systems here, or precipitation is coming from other processes that we do not capture really with these convective events. So that's another open question for future research. And now finally coming to the diurnal cycle, which is very interesting here. This plot here shows the local time of maximum occurrence of convective events as a function of space. And you see that it's very clear the contrast between land and ocean. So over ocean, it's clearly a nighttime peak of convection. We know that that's the case, that's what we expected. Convection occurs over the oceans mostly at night, but over the continents, it occurs in the afternoon. That's diurnal heating of the surface. That's what creates convection mainly over continents. But not everywhere. So you see that there are some particular parts where we have nighttime convection over land. And the most well-known is here Maracaibo Lake, where we have this extreme peak in lightning as well. So so convection here in this region and also in the box just next to it is mainly nighttime nocturnal convection. The same happens here to the north of Colombia in the lower Magdalena Valley and in the middle Magdalena Valley as well. Here, this part is also full of nighttime convection, even though this is just land. There is no lake there like in Maracaibo, but this is really land and we have a lot of nighttime convection. And this is something that has been noted by previous researchers before, but it hasn't really been studied in order to understand what really causes it. So here you see the different distributions of in terms of local time when these convective events occur. For example, here in this part of the Caribbean coast, it's clearly an early afternoon peak, peaking around maybe 2-3 p.m. Or more like 3-4 p.m. maybe. Then in the Magdalena Valley, you see it's really nighttime convection, peaking around 2-3 a.m. perhaps. In the Maracaibo Lake, it's very similar, peaking 3-4 a.m. maybe. And then here in the Amazon basin, we have daytime convection in the afternoon, but notice that it's also kind of earlier than what happens to the west of the Andes. So there's also kind of a jump in the timing of convection along the eastern branch of the Andes. So it's slightly earlier here than west of the mountains. And finally, well, you can see that here as well, this is in 2-hour intervals, how the convective events distribute along this region. You see that most of them are centered here in the early afternoon between 2 p.m. and 6 p.m. maybe. But then there's these very interesting locations where convection starts to pop up at night. So it starts first between 10 p.m. This is Colombian local time, of course. Between 10 p.m. and midnight, it starts in these 2 eastern flanks of the Cordilleras that I talked about at the beginning. It starts exactly there. It's kind of, they are in phase, both of these places apparently. And then it moves further throughout the Magdalena River Valley and towards the Maracaibo Lake, again here, you can see that. And finally, this peak of convection along the Pacific Ocean, offshore the Pacific Ocean, which that has been recently studied a lot. And we know that that's also nighttime convection that happens there. It's a lot of interesting mechanisms behind it that people have brought up, in particular Brian Mapes in 2003, with this mechanism with gravity waves created by the Andes and kind of explains why this convection eventually pops up late at night. And that brings me to the conclusions, which are more like open questions. So on the first hand, I identified several locations of interest for future investigations that could be of interest for many people. We found a lot of nocturnal convection over land, in particular along the Magdalena Valley, which hasn't really been investigated. We do not really know what are the mechanisms that force it. Then there's this question in the Amazon and the Orinoco basins, where we have a bimodal distribution of convection, but we know that there's a unimodal distribution of precipitation. So we need to figure out how to put those two things together. And some other things I didn't really mention here, but there's a sea breeze regime at the Caribbean coast, where probably the Sierra Nevada, this very high isolated mountain to the north of Colombia, it probably has an important impact there. But it hasn't been studied either. And then regarding the Colombian Pacific region, well, what we find here is essentially consistent with the recent findings by like what John Mejia has been working on, and Johanna Yepes as well, and all these recent results from the OTREC project. It's really consistent with all of that. And just to finish now, this has just been published. It appeared a couple of days ago. You can take a look at it in the quarterly journal of the Royal Meteorological Society. If you need access to it, you can always write me an email and I will send you a copy, because unfortunately it's not open access, but maybe through your institution you can also get it. Otherwise, just let me know. Thank you very much, and I'm open for any questions. I'll leave you with the conclusion slides.
Thank you, Daniel, for the very interesting presentation. And if somebody has a question, just go ahead.
Well, can I ask?
Yeah, go ahead, Ivan.
Okay, so very interesting, the results and so on. Did you also make some comparison with modeling? I mean, how successful are the models compared to your diagnostic?
Yeah, well, I haven't looked at any models right now. I just looked at this, based everything here essentially on the satellite images. Models tend to, from what I know, I haven't done it myself, as I said, but what I know, they tend to reproduce like the larger scale features relatively well, like this peak of convection along the Pacific coast, which is the most prominent one. But then the smaller scale ones, if you notice, many of these, many of these small hot spots of convection, you would really need a very high resolution model to look at that. That would be a next step to look at, see how, for example, a regional warp simulation would work on there. But
so do you plan to do something like that, or?
I think that we lost you just 15 seconds ago.
Okay, can you hear me now?
Yeah, it's okay.
Okay, so did you hear my answer? I don't know, my connection was unstable.
No.
For some reason. Okay,
yeah, the last, I mean the last part of the answer. But did you hear the second question from Ivan?
No, I think I didn't hear the second question.
Okay, so do you plan to make some such comparison? I mean, it would be a great data for verification for models.
Yeah, well, that would be an interesting project to work on. I think we will do that in the future, but I haven't started that yet. Yeah, that's definitely worth trying. Absolutely.
Yeah, well, I know that brightness temperature could be a little problematic in terms of determining the height of the clouds and stuff like that. But I suppose it would be possible to compare brightness temperature predicted by the models with what you have?
Yeah, you can. I mean, there's sometimes these satellite simulators within the models that you can try to reproduce what a satellite would see with the model output. So that would be a good way to do it. Yeah.
Okay, thanks.
Thank you.
Yeah, I have a question, a follow-on question. I wondered, I have no idea, like in Europe, we have got the Cortex initiative where we have climate simulations, I think at 12-kilometer resolution. So I wonder, is there something similar for South America? And is it still the core?
Yes, I don't know exactly how it works right now, but I just heard about it a couple of days ago. It's called Andex. And it's for, I think it's entire South America, something like 4-kilometer resolution as well.
Oh, really?
It's a project that is just starting. So that's a good way to look at this. Absolutely. Yeah.
Okay. Any further questions? Okay, I guess that is not the case. So Daniel, thank you very much for the presentation again.
Okay, thank you.
Great. So I think that we can move to the next presentation. It will be given by Yue Tian. Yue is a PhD student from the Frankfurt University, and she's mostly interested in foehn over the Alpine region in Switzerland. And she's going to present a station-based evaluation of the South foehn in the Switzerland simulated with a Cosmo 1 model. So Yue, and the floor is yours.
Yeah, I just noticed that seems like I cannot share my screen because it says the host disabled. Yeah.
Yeah, you are a co-host now.
Okay. So yeah, thank you for inviting me and introducing me. Can you see my screen now?
Yeah, perfect.
Great. So my topic is a station-based evaluation of South foehn in Switzerland simulated with Cosmo 1. So what is foehn and why do we care? So foehn by definition is a warm, dry, gusty wind descending on the lee side of a mountain range. So it is also a type of downslope wind. And you may also know this by its other names like snow eater or Chinook wind in North America, or Zonda wind. Maybe you are familiar with it in South America at the Andes. And in history, the highest wind speed ever recorded in Alpine Valley was 130 kilometers per hour, and the temperature can increase by up to 25 degrees Celsius in just 1 hour. So with these extreme wind speed and temperature, you may imagine the social impacts, like it can have a higher risk of fire danger, or it can cause severe traffic incidents, or it can cause, for example, like in Switzerland, because in the foehn valleys, we have this rapid snow melting, and autumn foehn events can really favor the agricultural activities. And it also causes air quality issue. For example, the ozone levels increase rapidly with this at the same time with the temperature increasing is a sign of foehn breakthrough in the valley. And it also can cause avalanche or glacier melting at Antarctic, for example. And some people also reported that they have this headache, foehn-related symptoms, and so on. And what is the mechanisms causing foehn heating in the downstream or foehn valleys. So you may be familiar with type A and type B. So for type A, we call it isentropic drawdown, where we have a cold inversion on the upstream side of a mountain, and then only the potential warm, dry air from upper level can cross the mountain and descend with dry adiabatic substrate. And from type B, I think you may know this from your textbook, that we have moist adiabatic lifting on the upstream side. Therefore, we have extensive precipitation and clouds here. And after it crossed the mountain, which normally here we have a foehn wall. So you see that the cloud stops right here on the mountaintop. And then after it crossed the mountain, it descends again with the dry adiabatic substrate. And so another two types is this mechanical mixing, is when we have this type A, we have this potentially warm, dry air on the top, and in the foehn valley, we have a cold pool. And in between of these two layers, we have wind speed or wind shear. It causes turbulence, and then it rolls this cold pool from top to down. And with and this type D, we call it radiative heating. Is that when we have a type B foehn, we normally on the downstream side, we call it foehn window or foehn clearance, is that it's very dry, so there's no cloud, very sunny, so the solar radiation is able to heat up the ground and erode the cold pool from bottom to the top, and then it allows the foehn flow to descend to the valley bottom. And so the project I'm working on is actually a collaboration between ETH Zurich and Goethe University Frankfurt. And as you can see, we are trying to cover a very broad range of all the processes related to foehn phenomena. And from ETH side, they are using trajectory studies. So they study more like a larger scale from a Lagrangian perspective. But in our side, we focus more on the processes in this valley, so shown with this red square, and we more focusing on the meso to small scale and using from a Eulerian perspective of view. So you can see that this includes the interaction between foehn and the land surface, and with the cold pool in the valley. And we will also evaluate the scale of NWP model. So in our case, it's the Cosmo model in its representation of near surface foehn flow. And in this presentation, I will mainly focus on number 6. To give you some background, so we have these anecdotal evidences of model biases from the forecasters, or from here we have 2 master theses with Cosmo model. So the pre-foehn cold pool in the model is usually too warm or too weak, and therefore it causes an early breakthrough to the surface in the model. And also during the foehn hours, normally it is too cold and too moist. Like the foehn flow is cold and moist in the model than in reality. And in terms of foehn extent, it is always too far northward in the model. So this makes us really want to study and try to document the biases that Cosmo have, and we try to we want to know if it's systematic or not. So we will evaluate Cosmo with first case study and then climatology study. And so the second question is, what could be the possible causes? So we designed several sensitivity experiments, which we will see the result later. And this is the outline of this talk. So I will first talk about the methodology, and then I will mainly introduce one case to you on the model biases, and then compare it with the other cases. And then I will study the biases more from a climatological view or study. And in the last, I will talk about the possible causes by sensitivity experiment. So we are using COSMO model. It is a non-hydrostatic limited area atmospheric model, and it is used operationally by many weather services in Europe. And by COSMO 1, it means COSMO with 1.1 kilometer resolution. So we are using the model setup quite close to the Mitchell Switzerland operational setup, including 80 vertical levels, for example, and the domain is also close to their setup. And we use station observations from SwissMetNet and sounding at Milan from University of Wyoming. And we use COSMO analysis data for two purposes. So first, we use it to initiate the simulations. And also we are using a longer time period of this analysis data to study the foehn climatology or the foehn bias climatology. And here on the left, you see the model domain. And on the right side, you see the locations of these stations. So mainly the station observations from the north of the Alps, because we are studying South Foehn, and one sounding station at Milan. Here are the cases we chose. So we try to cover different characteristics. So for example, the case from 2016, we have a very long and strong foehn case, and we have two cases from 2013. One is a dry foehn case, and the other is a moist case with excessive precipitation on the upstream side. And we have two cases from 2017, and they are with different synoptic situation. And here is the detection method we're using. So we mainly taking the wind speed and humidity as our measurement, and we apply this to criteria to both simulations and observations. And as you know, the model has bias, so we get different foehn hours from simulation and observation, and therefore you will see this common foehn hours is just we took intersection of the observed and simulated foehn hours. Okay, so the first case I'm going to show you is 2016 November case. So from synoptic situation, it has a quite typical foehn synoptic setup. So you see a low pressure on both 500 hectopascal and on the surface over the British Isle. And on the east side, we have a high pressure. And therefore you can see a very crowded isobar over the Alps in the surface pressure shown with this colorful shading right here. And what makes this case extremely long is that so on the right side, I'm showing the weather map after 4 days, then after the left one. So you see here low pressure is cut off from the main current. So it basically maintained at this location, even though the main current is keep moving to the east. So therefore, this cutoff low helps to maintain the pressure gradient over across the Alps right here. And if we look at the stations in the Foehn Valley, so on the southern side of the mountain, and I'm showing you 3 stations. So first you can see there is a longer Foehn duration in simulation shown by this blue thick bar on the x-axis than in observation showing by this gray box calculated with this the criteria I just showed you. And then we can see a very significant cold bias and moist bias in relative humidity during Foehn hours. And you can see this cold bias and moist bias in the other stations too. And another thing is so we can see that the model, which is shown by this blue curves, fails to capture the temporary retreat in the middle of this event at Oberried. And at Altenrhein is the stations basically very far to the north. So in the downstream of the valley, you have this extremely long Foehn period in the model, but not in the observations. So you could imagine that the model actually overestimate the Foehn extent in the lower Rhine Valley. We could look at this also from a cross section during this temporal retreat, or just a snapshot at this temporal retreat moment. So you see in the model, the Foehn front is actually very far to the north, but in the observation, which is shown by these dots here, with the same color map, the Foehn is actually somewhere in between these 2 stations, so very short, shorter than in the model. And this is the same in wind speed field. So you see this far extent, the maximum of this wind speed here too in the model, but not in the observations. And if you look at the vertical cross section, you can see that so behind this elevated area, you have this mountain wave structure right here, basically intensify the wind speed or the potential temperature at this location. So Altenrhein, so this location. And if we involve more stations on the northern side of the Alps, we can see most of them or all of them have a cold bias at the magnitude of around 3 to 4 degrees Celsius. And now let's compare it with the other cases that are chosen in this study. And when we involve even more cases, we can find still a cold bias here, even though with different magnitude, but in average, still around 2 to 4 degrees Celsius. And in terms of, so before we observe this moist bias in relative humidity, but here in the specific humidity, you don't really see a tendency of moist bias or dry bias. So we could say the moist bias in relative humidity mainly caused by the cold temperature bias. Since we observe this very constant cold bias in the valley, we want to know if there's also bias exist on the upstream side. So now we are looking at the sounding from Milano. And here I calculate the bias between sounding data and the Cosmo 1 output or results for the average of these 5 cases. And we need to make sure that we are looking at a higher level, like a level around mountain crest, because you know that in most of the cases, the foehn comes from a higher level, from the upstream side. Therefore, so the Alps is around more than over 2 kilometer height. So we can look at, for example, over 800 hectopascal. And then you can see, well, you can say a cold bias, but it's quite small. I mean, it's less than 1 degree Celsius, but if you compare it to the previous cold bias we found in the valley stations, that's 3 to 4 degrees Celsius. So we could say it doesn't seem like the bias is originated from upstream, or it only contributes a very, very little to the bias in the valley. And so here I'm showing you is the Cosmo 1 analysis that we use to initiate these simulations. And then you can see that for the 3 cases we have, so the Cosmo 1 analysis is quite similar to the result. And as you know that so as far as we know that the Cosmo 1 analysis didn't assimilate the temperature. Well, it only assimilated the surface pressure and dew point temperature and the sounding data. So it's not a big surprise that in terms of temperature, we have this like very similar pattern between Cosmo 1 analysis and Cosmo model during foehn. And therefore we can take advantage of it because we have a very long-term Cosmo 1 analysis data. So we could use this data set to study the foehn bias climatology. And if you calculate the bias in temperature over this 5-year period during common foehn hours, you can see the cold bias again. But during non-foehn hours, we don't see a cold bias. So we can say that this cold bias is quite something special during foehn events. Okay, so there are several possible causes proposed in the previous study about this cold biases. For example, in the valley, the atmosphere coupled too strong with the soil, with the cold soil in the model. Or for example, there's not enough turbulence in the foehn valley, or the atmosphere is too stable to mix up the atmosphere. Or we have not so accurate roughness length in the model, or we don't have enough heating due to the smooth topography over mountain in the model. And so therefore I designed some sensitivity experiment, mostly focusing on the second point. So I will not go through all of these experiments, but just give you an idea. So the first 2 experiments is aimed to decouple the atmosphere from the cold soil. And the third one is just a better representation of the surface processes, the bias soil evaporation. And the fourth one, so the TKE model or the TKE scheme used in Cosmo is 1D model only considering the vertical production. And now we are trying to include the shear production, like including the both horizontal and vertical shear production for the TKE prognostic equation. And the last one is we simulated all the cases again with even higher resolution, so Cosmo 505 meters. And here is an example. So the time series for temperature for 2017 March case. And then we see that most of the sensitivity experiment doesn't make a big, like doesn't have big differences between all these sensitivity experiments except for the Cosmo 500 meters. And it has a smaller code bias. And other sensitivity experiment, for example, the skin layer, which is to detach the atmosphere from the soil, we have a larger impact prior to the foehn event, so during the cold pool stage. And if here's another example for the Cosmo 500 experiment. So we see that at this moment, for example, we have cold pool, the foehn front quite to the north right here. Therefore, we have very strong cold bias at these two stations. But in Cosmo 1 model, at the same time, the foehn front is shorter. And therefore, you see a better result, a smaller bias at Rhine station. And it comes to the conclusions. So first, we observe this cold bias in surface temperature in both our case study and climatological study. And the lowest bias in the previous studies in relative humidity is mainly due to this cold temperature bias. And in terms of specific humidity, we don't really see a lowest bias tendency. And the cold bias in the valley is unlikely due to the upstream bias. And by doing those sensitivity experiment, we don't find any significant improvement. So which means that if we decouple, it doesn't really make a difference if we decouple the atmosphere from the soil during a foehn event or so, except that we do see an improvement in Cosmo 500 meters. So it not only has a smaller cold bias, but also in terms of foehn extent, yeah, it is improved. And yes, that's the end of my presentation. Thank you for your attention.
Thank you, Yue, for this nice presentation. And if somebody has a question, go ahead. Yeah,
So when you did the simulations, sorry.
No, go ahead.
When you did the simulations, did you restart them, or was it like a few days simulation?
I think I only do restarted in the first case, like in this very long case, but the others, yeah, for the others, I'm able to finish it in one run.
So how long are those runs?
I think 3 hours or 5 hours for the shorter cases, and for the longest cases, maybe 8 hours in total or even longer.
But I thought it's a multiple days event. At least at the end, you showed multiple days.
Mm-hmm. Yeah, but with Mistral, yeah. I am able
you mean to... No, I mean, I think that the question is more about how long is the episode in physical time.
No, I wanted to know how long is the simulation which you did.
Yeah, the simulation is... Yeah, sorry.
How long is it?
It's around 3 hours, like 3 hours to 8 hours, I think.
Really? Because the spin-up is just around 3 hours, usually. I don't know.
Maybe it's not like as high resolution as yours, and
I think you're
also
talking about
limited
different
regions.
things. No,
Yeah, I
Volkov
suppose.
time and simulation time.
I mean,
I'm
node hours or the
I'm not
simulation
interested
time.
in node hours, no. I'm interested in how long is the integration time.
Yeah, it's here in this slide that it's showing here the time span between for the simulations. So the longest one, correct me Yue, if I'm wrong, it's the first one, isn't it? It's around 6 days.
So could you show
exactly.
again the picture where you showed the performance when you did the sensitivity studies?
Okay, so I'm guessing you're talking about the last slide.
Yeah.
This one.
No, another one.
This one.
No. Yeah. For example, this one. Yes. So it's like how many days is it? 7?
Yeah, 7 days.
Okay, so my question is this one simulation? Or did you do restarts in between?
I'm not so sure, but I think in this case, I restart the run, but it's just automatically done with the script, so I need to check.
Okay, so and now I come to my actual question. So because this one day when you have improved Cosmo 550 meters, could it be caused by a restart?
You mean at this moment, for example?
Yes, exactly. Because it looks like that, and then it returns to a different regime. Just a question. I don't know the answer.
I don't think so. I don't think it restart that frequent, at this point. So
no,
I don't
just to
think
make
that's
it clear,
the
there might be a restart, but there's no reinitialization. So it's just one long simulation.
Okay, so it's not really a restart, it's just like extending the simulation because of computational reasons.
Yes. Mm-hmm.
Yes.
Okay, so that's not a restart, at least for me. Okay, thanks.
Daniel, if you would like to place your question.
Okay, so thank you, Yue. Very, very interesting talk. I was just wondering, so do you think this is just a matter of resolution? So if you go to, I don't know, 50-meter resolution, maybe you will solve this bias? Or do you think maybe it's something with some other parameterizations that you haven't looked at? I was thinking maybe, what about the radiation scheme? Have you thought about that?
Oh, I didn't really look into the radiation. Like I didn't compare the radiation model to observation. I could do that, but I didn't do that yet. Regarding the other parameterizations, we are actually thinking probably the turbulence could be a bigger causing this problem, probably because as I think. So in the sensitivity test, you see we only try this shear, so increasing this shear production for TKE, but it is still not let's say 3D TKE scheme. So it is still basically just made some minor modification on a 1D TKE model. So we are now thinking this probably could be the issue. And also, if we look at the profile in the potential temperature profile in the valley, we could see that. So in Cosmo 1, it is, even though during a foehn case, it is still somehow weakly, stably stratified, because I mean, in the foehn period, we are expecting for a well-mixed atmosphere, but in Cosmo 1, the atmosphere is still overall within stable stratified. So, and with Cosmo 500, it is actually improved a little bit. So that's why we are, suspecting that probably the turbulence scheme could be one of the reasons.
Okay, yeah, that makes sense. And just one last question: how often do these foehn events occur? Is that something that happens, I don't know, twice a year, or is that twice a month, or I don't know?
So it could be, I think, no, it's definitely more frequent. Like, for example, in spring or in autumn, it could be quite frequent, like every 3 or 4 days. There is an event, and it could last just 3 hours. It could last for a few days. It really depends. So, but it normally is more frequent in spring and autumn. And in summer and winter, I think the frequency may be lower, but at least every 10 days around, or every half a month.
Okay. Okay, thank you.
Finally, we have time for a quick question. Shweta, if you would like to place your question.
Yeah, thanks, Yue. Actually, Daniel already asked that question. So, but I was just curious. So my first question was whether you will go to more finer resolution in your setup, and can you say that this will actually solve the coal bias issue or not? One question was, is it in the online setup, the two 1 kilometer or 500 meter, or these are two independent runs?
So the first question is that I'm not so sure if it is necessary to go to higher resolution, because I mean, this is for operational purpose. I think it's first because we find this in our operational usage from the Weather Bureau, for example, and I don't really know if they would like to see a resolution like that. And then, I mean, but if it is just for purely scientific research purpose, well, we still need to see, because that's actually our next step to see if we have this bias in icon, or if we will run this with icon LES, for example. And I'm not so sure yet, but we can keep track on that.
Okay, good. Yeah, that explains. And are the two setups, Cosmo 1 kilometer and 550 meter, are they in the same nested run, or it's two separate runs?
It's two separate runs. We don't use nesting technique.
Yeah, just like maybe a very crazy idea. So do you think it's a problem with the physics or the dynamics part? I mean, foehn, I mean, I don't know much about the it's the dynamics itself, but could you try like different advection part, like how is it treated in Cosmo? Do you have options?
Advections.
Yeah.
I don't know. I think the dynamic part is settled. It's set in Cosmo. I didn't think about that. But for physics, like turbulence, for sure. I mean, there are not so much options in Cosmo, just a minor modification, as I showed you right here, by increasing the shear production. And, yes, so there is a 3D scheme in Cosmo model, but so far I don't think it works. So I run, but it doesn't work. Yeah, but I don't know about the dynamic part.
Okay, yeah, but thank you.
Thank you.
Okay, so thank you, Yue, again for your presentation. And now we can move to the final presentation of today. It will be given by Alejandro Casallas. He's a PhD student in atmospheric physics at the International Center for Theoretical Physics in Italy. His work focuses on the use of idealized simulation to analyze the role of microphysics schemes and color pools play in the convective self-aggregation. So Alejandro, the virtual floor is yours, so go ahead.
Hi, Julian, thank you for that good introduction. So first of all, I would like to thank Daniel and Yue for their presentation, and also Julian for inviting me here. So can you see my presentation now?
Yes, we can.
So, okay, my talk will be going about the role of microphysics schemes in the organization of convection. I'm here in the ICTP doing my PhD for 9 months now. So this is work in progress, and I'm working with Adrian Tompkins, and now with the help of Greg Thompson. So first, a little introduction about it. So I don't know if you know, but convection likes to be organized. So you can see, for example, the scale lines or mesoscale convective systems like these ones, or you can even go to larger scales and see tropical cyclones or equatorial waves, and even in planetary scales that you can find the Madden-Julian oscillation, for example. So convection likes to be organized. But why this happened? And there are several reasons, and in the larger scale, there are several dynamics and everything. So for example, one of them is the sea surface temperature. So in the warmer places, you get more convection because it's warm and moist, so it favors convection. The wind shear is also important, for example, to organize the convection in a skew line wave. And wind shear is simply the change in wind speed with height, that you can see here. So when you go higher, wind speed is faster. And it's a completely different one is convective self-aggregation, that it's convection likes to organize without any external force. Like, for example, you have the same SST, or you don't have wind shear, or you remove rotation and everything, still convection likes to organize. So why is the case? So to understand this, normally we use radiative convective equilibrium. And radiative convective equilibrium have been used a lot in the past. So what it is? It's when the atmosphere it's in a radiative convective equilibrium state, which is a fight between radiation that wants to be in radiative equilibrium and produce a very unstable atmosphere, and convection that balance that equilibrium and tries to have a neutral atmosphere. So to describe this a little bit more, this is a plot of Manabe and Stickler. Manabe won the Nobel Prize in Physics this year. So they show that in a radiative convective equilibrium atmosphere, which is this line, I hope you can see my cursor, the surface is too warm. You see, it's 340 Kelvin, so it's too warm. And the tropopause is too cold. But here, the stratosphere, it's very well represented. So it's very similar to what you would expect to see in observation. So what happens if you take that model and you add, for example, sensible heat transport, and you will get the dry adiabatic adjustment, that is this one in the middle, but you still have very warm surface and a very cold tropopause, sorry. So you still need something else. And another important aspect is that the lapse rate, that is like the steepness of this line, it's very high in these two models, but this it's better, and it happens when you add moisture. So when you add moisture, you get this line where this surface is more similar to what you will see in observations, and the tropopause is also warmer, what is what you expect, and the lapse rate, that is the change with temperature with height, is of 6.5, that is more or less what you get in observations. So this tell us that moist convection is important. So, but why is important? It's important because it redistributes the water vapor. So it moves it in the vertical, the water vapor. It produces phase changes. So for example, it produces clouds when the water vapor rises. It condensates and produce clouds. And the clouds have radiative impacts. So there is like an interaction there that is important. And they also control updraft and downdraft. So the updrafts are really small, but they are really powerful. The clouds beneath them are really powerful. The updraft and downdraft are really not that powerful, so they need a larger area to succeed and balance those updrafts. And I want you to notice that it's very important that radiation, to notice that radiation and convection are highly interactive. So what kind of people have been using this and why? So RC simulation have been using 1D setup by Moller, Manavan, and Stickler. In 2D, and you have here an asterisk because Held et al. In 1993 found convective self-aggregation for the first time in a simulation. And in 3D, and Tompkins and Semi and Craig were the ones who found convective self-aggregation in 3D simulations. But how it works? So imagine you have a box like, and you have two layers. So one is the ocean, and the other one is the top of the atmosphere. So the ocean has a fixed ST, so you put, I don't know, 28 degrees, 29, 30, whatever you want. And the solar radiation is constant. So it's the same everywhere. And what will happen if you let it run and pass some time, you will get convection, and the convection normally likes to organize. It could be that it doesn't happen, but normally it happens. So how is the dimension of this box? And normally the dimension is 100 kilometers by 500 kilometers. And in the vertical, it is more or less 25 to 30 kilometers. So to illustrate this a little bit more, I want to show you this video. Let me try to do it. I hope it works. So let me know if you hear, but I think it doesn't have any noise. But what you are seeing is clouds and precipitation, no? So you see that it's completely random, no? It's completely random in the domain. But then you will start see that one place stops to produce clouds. So you can see there is random, but this place doesn't have any type of clouds, you see here. And this start to grow and grow and grow and grow. And if you go a little bit farther, you start to get a line of convection, and here you don't have any type of convection. All the convection is here. And if you wait a little longer, you end up with a blob of convection like this, like a bubble of convection, so to say. So that's how it works. And several people have worked on this. And they even have produced global simulations to understand mechanisms, and even Joe Charney have done it. So simple models that appear to contain the main physical factors are important. So why is this happening? So dry regions get drier and moist regions get moister. Why? Because moist regions are favorable for convection, and dry regions are try to remove convection and not let it happen. And you also have long wave and surface flux feedbacks. And the long wave feedbacks are produced because in the dry regions that don't have clouds, the outgoing long wave radiation increase, and when it increases, it cools and produces more sinking, and more sinking there, but the other place that has a lot of clouds start to be warm, more moist, and more moist produces more convection. And the same thing happens with the surface flux. When you have a cloudy region, you have gustiness, more gustiness than in dry regions. and that ghostiness evaporate more water and produce a favorable place to convection to happen. And there is also a moisture memory. So if you remove the long wave radiation, for example, sometimes convection even organized because moisture likes to be together. And why is important? So it's important because you change the large state of the climate. So if the OLR, if convective aggregation increases with warming, for example, you will get more outgoing long wave radiation and you have a negative feedback in climate. But if convection starts to be more random in a warming climate, so you will have less OLR, so a positive feedback will happen. It's also because you have a change in clouds. The synchrone region is larger, so the clouds are different, and they have even found that high clouds are the ambials start to shrink a little bit. And when convection is organized, you got a mean warmer atmosphere. So all of that, sorry, have led us to the RCME project that you can find in Wink et al. 2018, I think in James, I don't recall, but I think. So they have run a lot of models in the RCE state and see what happened with those different models and different parameterization and everything, but trying to be as similar to each other. And they found, and it was also found that with Thompson and Semi in 2017 in James, that aggregation, it's sensitive to the parameterization. So for example, in Thompson and Semi, if you change the diffusion coefficients or the diffusion parameterizations, if you use TKI or if you use Magorinsky 2D or if you use Magorinsky 3D, you could prevent or enhance organization. So you can see here one of like some tests to show you that you have a lot of difference only changing some things. So WRF, it's good because you have a lot of parameterization and things that you can use to make sensitivity tests. And here what I want to show you, this is the cloud fraction with high, this is the vertical profile of heating rate and related humidity. And the only thing I'm changing here is the diffusion coefficient. So if you want to have a 2D Magorinsky scheme or 3D Magorinsky scheme, how the results change. And you can see that they change a lot, no? And even if you add an extra diffusion, a numerical diffusion, thing, you could produce, for example, this type of melting level clouds that doesn't seem very, like they are not something that we would expect. So this tells us, okay, parameterization are important, so let's study them. That's what I'm doing now. So I have I'm using WRF with a domain of 100 by 500 kilometers with 63 vertical levels and a resolution of 6 kilometers. So it's convective per minute simulations with a top in 25 kilometers. The idea is not to change the long wave radiation as shown with radiation or the iCloud, PVL, or eddy coefficient. And we also have a fixed SST. But we want to change the microphysics to see how sensitive the convective aggregation is to the microphysics. So if you see here, you are seeing OLR, and each column is a scheme, and you see here day 3 and day 45. So you can see that Morrison is organized, WSM is organized, GC is organized, Lin is starting to organize, but Thompson is not. And you know something is organized because you see an enhancement in OLR here, and the convection only in a line or in a plot. But to know that it is organized, there is a metric, and there are several metrics, but I decide to use here the interquartile range, that is the 75% of water vapor minus the 25 percentage. And when you have a quick change, a steeper change here in the interquartile range, you know that you have organization. So here you see, okay, for Morrison, WSM, GC, and Lin, we got organization, but not for Thompson. So why? And there are several reasons that could be producing this. One of it is the ambles. So Bretherton, in a seminal paper in JAS, showed that the ambles are really important to prevent or make quicker the organization. So we can change the ambles. And how can we change the amble? Changing the fall speed of ice. So if we change the fall speed of ice in one or two of these schemes and see what happens, we can know how sensitive they are to organization. And we can be prevented, no? That's what we are looking for. And the other thing is changing the low clouds. And this have been made by Copin and Boni, and they indeed have theory about it in which the feedback that the low clouds produce is essential to get organization. So the other thing that we can do, and it's what I have been focused on this first step of the project, because I have run these simulations, but they are still running. We go to the cold pool size. So when you have larger cold pools, you are homogenizing the domain. Why? Because the cold pools tend to take the moist and redistribute it to the drier zone. So if you have larger cold pools, you would expect to get less organization. If you got smaller cold pools, you will expect to have more organization. And several authors have done something like that. They change the evaporation of rain, and here I put only 5, but they remove completely the evaporation of rain. So they are removing the cold pools. So we want to go one step further, because they all have found that the cold pools are important to prevent organization, and when you remove it, you get organization very quickly. So we show that that's true completely. If you remove the evaporation of rain, you get organization really quickly in all the simulations. But what happens if you halve it? So if you halve it, you get organization as you would expect, no, in the majority of the schemes, but not in lean. And this is weird. Why lean is not organizing? And we don't know. But it's even weirder, because if you don't change the cold pools, you let it a little bit larger, you get organization. And if you double it, you get organization in lean, but not, for example, in GCE. That is what you would expect. And even if you see Morrison organized less than before. So why? Why is this happening? Why lean it's organizing if we double the operation of rain, but is not when we have? And this was one of the more difficult questions, because it's not very easy to know, but there is a paper by Young in 2019 in which he used an available potential energy budget to quantify, for example, convective heating. And my idea was, if we are changing the operation of rain, we are probably changing convective heating. If we change convective heating more than or less than, it's more important to change convective heating than the cold pools, so you will get or not organization. It's like a fight. It's like a fight in which if you change the operation of rain, you will change cold pools, but also convective heating. Which change the most will determine if convective will organize or not. And we calculate the budget, and this is the case. So now, and if this will be in presence, I will ask you all to think about how to do. How could you now make a test or experiment to test the cold pool size without changing the convective heating? And this problem takes us a lot of time to think and read and everything, and we come up with something that, thanks to Grant and Van de Heever, that have a good result, an amazing result that will help. So what you are seeing here is, or what I want you to see here, is that this is a cold pool ring, okay? So these lines are the wind. Here you see also a wind, and this panel is if you add land, and without land. So without land, the cold pools reach 36 kilometers, but with land, the cold pools get to 25 kilometers. So with land, the cold pools are smaller than without. So why is that? And the reason is the sensible heat flux. So for some reason, in land, the sensible heat flux start to act really fast and start to recover the cold pool really fast, so it cannot reach like 36 kilometers, like without any land. So now the question is, how could us use this property inside Earth? So this is normally what you will get. So you have here the surface fluxes, and they are recovering in time inside a cold pool, no? And what we would like to do is this. We want to enhance it or put it a little bit slower, no? And the way is to change U. So if you change the wind speed, you could produce it, but that has a problem. And is that if you change the wind speed, you could mess up a little bit the momentum equations. So what we are doing is taking advantage of the Monino-Bikov similarity theory. I'm sorry if I didn't pronounce it correctly, but what they did in the model is they have the wind speed, they create a copy to use in the calculation of the surface fluxes throughout the Monino-Bikov similarity theory. And that U is the one that we can use without messing up the momentum equation. So this is a way that we are coming up to do it, but then must be other ways that we can think about it. And if some of you have any ideas, it will be great. And we test it, but to test it, we say, okay, we only want this to change when the downdraft are present. So when the buoyancy is negative. When the buoyancy is negative, the idea is to increase the wind speed so that the surface fluxes increase and the cold pool recovers faster and its size gets smaller. And we test it and it works. It works really fine. The vertical profile doesn't mess up anything. The cold pools recover faster and are smaller. Now we are testing it to see how sensitive is the organization to the cold. So some key aspects that I have coming up are the diffusion and the empty schemes produce really large uncertainties, and that's really important, no? Because if you only change the microphysics, see how different are, for example, the Anvil's percentage or the low clouds, no? So this is one of the main variability that you get in, for example, climate change models in synaptics and everything. Other thing is that if you change the operation of foehn, you will modify to modify the cold pools, you will increase or decrease the convective heating, and the convective heating can be calculated with this. That is a part of the A production in Young, where S is the buoyancy sources, B is the buoyancy, and this line is the slow component that is like a moving average, and this is the domain mean. N is the root by Sala frequency, and rho is the density. And that one alternative is to change the cold pool size, because it could decrease or increase the surface fluxes, and in that way we can recover faster cold pools or slower, and see how sensitive the aggregation is to this. So if you have any questions, please, you can do it now, or you can write me if you're interested to me or to Adrian Tompkins. So this is our email. I don't know if you have any type of questions.
Thank you, Alejandro, for the presentation. So if somebody has a question, just go ahead. Ivan, go ahead.
Yeah, I have two questions. So, or first is suggestion. So you mentioned Monino-Bikov and that you use it somehow. I didn't get it how to modify the wind. So basically, you can change your roughness length if you want to do it through surface turbulence fluxes. Meaning that when you have, I don't know, more trees or whatever at the surface, it slows down the cold pool propagation, and maybe you get what you want. Okay.
Yeah,
so
the only problem there is that we have only ocean, and it's a good idea, but I don't know how you can only change it in the corpus, no? Because you will need to change the some survey.
Basically, you change surface, only surface.
Yeah, but in that case, you will affect all the surface, not only the corpus, no?
Yeah, but it's more physical, right? How do you want to affect just, and the other thing is waves, right? If you have corpus, it generates waves and that increases roughness. I don't know how exactly is that parameterized in WRF, but there are schemes which can do that. So maybe you can play with that.
Okay.
Yeah, but you can do also overland, and then you have roughness.
Yeah, the problem with overland is that we don't know if we will get convection because the organization, sorry. But that's a good suggestion. In fact, that's something that we would like to do, like an ocean, like Iceland or something, and see what happens.
Yeah, for example. And the other thing is you study deep convection with the help of models which parameterize deep convection, right? So you understand that there are limitations of those things, and it would be great to have a model which doesn't need parameterization of deep convection. It's cloud resolving mode, you can call it, or even a large eddy simulation mode. So you could use those and maybe to minimize some uncertainties in your simulations, and then you could focus more on your microphysics because you don't know which part of that is just coupling between various parameterizations which you detect now.
But we turn off the convective parameterization because their resolution is more or less 2 kilometers.
So you are already using cloud resolving?
CRM, yeah.
Okay, I didn't get that. But...
Okay, no.
Okay, thanks.
Any further questions? Yeah, Daniel, go ahead.
Yes, so thank you, Alejandro. Very, very interesting. I would like just to ask a more fundamental question. Now that you've looked a lot into the model and changing different things, looking at different schemes, what happens with the microphysics, etc., etc. What would you think is like the main process behind the organization based on what you've seen? Is it the radiation? Is it the dynamics? Is it the thermodynamics? What do you have a feeling already of what the main process behind the organization of convection is?
That's a very, very cool question. But like my hunch is, so if I only focus on the microphysics, I think that it's the radiation. So my results have more or less showed that the radiation is really important because if you change the clouds and that maybe so only to see what happens, I use this setup. And if you see here, you are producing too much melting level cloud, no? And in a way, this was a problem and this was a mistake that we have to address because normally you will not get this. No? But it was interesting because you change that much the radiation that the feedback could not happen. And when the feedback doesn't happen, organization is really slow, or even you remove it. And in fact, in Thomson, you remove it because Thomson have too much ice and snow. And when that happens, almost all the domain is covered in cloud. So in the lower troposphere, you get a lot of outdrafts that then are removed in the upper troposphere. So you really get organization because of that feedback. But the other thing that is also really important is the diffusion, because you can even remove convective organization if you decrease the diffusion coefficient. So I think the radiation is the most important one, but it's like a merge of all of them. And in fact, if you put something extra, for example, there are other elements that could play a role. For example, there is a result, a great result that it's in one of the new papers of Adrian. Normally, SST is produce organization, no? But in the small scale, they prevent it because you get out in a place start to warm more because you have more radiation, no? And that place that is warming in the small scale try to move and prevent organization. So that's something really remarkable. And now we are seeing that existing observation, and in fact, it seems like the tropics like to be organized and could not be organized when some wind shear elements enter to play. So I think it's a combination of radiation and thermodynamics, but radiation is more important.
Okay, thank you. Yeah, very interesting.
Thank you, Daniel, for the question. I don't know if anyone have another one or any ideas about the topic.
Okay, so if there is no further questions, so I would like to thank the speakers of today. So thank you very much for joining the seminar, or the attendees as well. So this is the first one of our seminar series that we are planning for the remainder of the year. So very likely the next one will be around February. So yeah, we will let you know as soon as we have an agenda for that. So again, thank you very much for everybody. I hope to see you in the next one.
Thank you.
Yeah.
See you
Thank
next
you
time.
for organization.
Thanks, Julian and Daniel, for the organization. Bye.
You have a nice day.
Thank
Bye,
you very
Joaquin.
much. Goodbye, hola. Have a good success in the future. Ciao.
Ciao.
Ciao, Joaquin. Thank you.